Hey everyone, welcome back to Math 261. This is Scott. Let's get started. What we're going to be doing now is picking up in section 5.2 where we left off in section 5.1. Oops, 5.2. And so what we're going to be doing is figuring out how to figure out the eigenvalues. So in section 5.1, we were already basically told the eigenvalues and we proceeded from there, or else we were specifically talking about a triangular matrix. But now here's a more general approach that will work for other situations. So this is what's called the characteristic equation. So the characteristic equation. All right. Well, let's think about things. So suppose we want the eigenvalues of a square matrix. So that's our setup. We have A and n by n. So square. So the goal would be find the eigenvalues of A. Well, let's think about what that would mean. So an eigenvalue, so recall, if lambda is an eigenvalue, of A, then A minus, well, let's actually go down the chain of reasoning again. You can't write it too many times. It's always good for you. So then AX equals lambda x for some x not equal to 0, not equal to the 0 vector, which then means AX minus lambda x is not the 0 vector. Sorry, is the 0 vector. Equals the 0 vector. Which then means that AX minus lambda I x is still 0. Which means that A minus lambda I times x equals 0. And that means that this has a non-trivial solution. So for this to have a non-trivial solution, then according to our invertible matrix theorem, if you recall, the most epic theorem that we've covered in this class, then according to the invertible matrix theorem, A minus lambda I must be singular. In other words, not invertible. So, if it were invertible, then there would only be the trivial solution. And in fact, you could see that because we could just multiply by the inverse of it on both sides, and we'd get the 0 vector for x. So that means it's not invertible, which means, so thus, the determinant of a minus lambda I equals 0. And now that's the 0 number. So this is called the characteristic equation for a, and then just the determinant itself is called the characteristic polynomial. So characteristic polynomial so this is the determinant of a minus lambda I. And the reason why it's called it a polynomial is because if you actually expand it out using cofactor expansion, for example, you'll get a polynomial in lambda. So expand this. Expand this to get a polynomial in lambda. And then the characteristic equation is what we just wrote up there. So the determinant of a minus lambda I equals 0. So set the characteristic polynomial equal to 0, and you've got yourself a characteristic equation. Now this will be a polynomial equation, and the solutions to it will be in fact the eigenvalues. So the solutions to this will be the eigenvalues. All right. Now, when we go about solving this equation, we are solving a polynomial equation, and we'll frequently be dealing with something that is either quadratic or only very slightly cubic. And so we should typically be able to solve it either by factoring or the quadratic formula. However, in real life, you're often dealing with a much bigger situation than a 2x2 or a 3x3 case, and so it happens that you have to solve those sorts of equations, and their various numerical methods are commonly used. And actually, there are also different kinds of numerical methods for finding eigenvalues other than what we are about to describe here. But it's a matter that those who need to know it will learn it when the time is right. So let's try some examples, and well, first let's describe the sorts of things that can happen here, and then see some examples of those things happening. So possibilities. So possibilities for what can happen. We might get distinct real eigenvalues, each with only a multiplicity of 1. So distinct real eigenvalues, non-repeated. Repeated eigenvalues, and here we'll really only be talking about repeated real eigenvalues, although it's possible that they can come in other flavors as well. And then finally, complex eigenvalues. Okay, so let's see some of these things all play out. So we won't dwell too much on the actual implications of each of these scenarios. However, we'll look at that more in sections to come, particularly the next section. But let's just try our hand at some of these situations. So, example: find the eigenvalues repeated according to multiplicity. Okay, so let's take as our first case something like this. So let's go with A equals 4, 6, 6, 4. All right. So in this case, what we'll have is so let's go through the motions so you can see what we have to do. So what we have to do is we have to figure out first what is A minus lambda I. And so this is a matrix that involves an unknown. 4 minus lambda, 6, 6, and 4 minus lambda. So then the determinant of A minus lambda I equal to 0 would mean we have 4 minus lambda times 4 minus lambda, so it's a determinant of a 2 by 2 matrix, nice and easy. Then minus 6 times 6 will 36. So with these, I personally find it more convenient to do to FOIL this basically backwards. So lambda times lambda is lambda squared. We have negative 4 lambda, so minus 8 lambda. And then we have plus 16. And then minus 36 equals 0. And what we get is lambda squared minus 8 lambda minus 20 equals 0. And so if we want to factor this, we could do this with a quadratic formula too if you don't like factoring for some reason. It's going to be minus 10 and plus 2 as the factors, which then we will get lambda minus 10 equals 0, or lambda plus 2 equals 0, which leads us to a lambda equals 10, 2, and they're each multiplicity 1. Usually we won't actually specify the multiplicity unless we're asked, or unless the multiplicity is higher than 1. And then if we were really feeling our oats, we could go further, and we could sorry, negative 2. If we were really feeling our oats here, we could go further and find the eigenvectors that correspond with these eigenvalues. But that'll be a matter for another section. We'll put all the pieces together. For now, we just want to get the things out there. Okay. So there's A. Now let's go with B. So this was a case of distinct real eigenvalues. Now let's go with something like this. So let's say that A is now equal to 1, 3, 0, 1. Okay. So what we'll have here is a minus lambda I. So this again means subtract lambda times the identity matrix. That's lambdas along the main diagonal. And so then that's going to be a 1 minus lambda, 3, a 0, and a 1 minus lambda. And then if I want to set up the characteristic equation, that would be determinant of a minus lambda I equals 0, which then means we would be talking about 1 minus lambda times 1 minus lambda minus 0 equals 0. And this is going to give us lambda minus 1 squared, 0. Because I could basically pull out a negative 1 from each of these, and that will then cancel out, and that will leave us here. And then this means that lambda equals 1 and 1. So it's a lambda. Another way of putting this is lambda equals 1 multiplicity 2. So it's a repeated eigenvalue of 1. All right. Now for case C, let's take A equals, as an example here, 2, negative 1, 1, 2. I think probably you can have some guess as to where I'm going with this. If the first one was repeated real, the first one was distinct real, the second one was repeated real. What's this one going to be? I don't know. Let's find out. So a minus lambda I will be 2 minus lambda negative 1. 1 and 2 minus lambda. And to set up the characteristic equation, we have to take the determinant of that and set it equal to 0. So 2 minus lambda times 2 minus lambda plus 1 equals 0. Now this is going to be a lambda squared minus 4 lambda, so plus 4 plus 1 equals 0. Now, those of you who are more comfortable in the algebraic world might be able to figure out some fancy way of doing this. But just to show you that no fancy ways are necessary, we can just kind of go with the nuclear option here, which is the quadratic formula. So lambda squared minus 4 lambda plus 5 equals 0. And so now what we have is something we can't. So if this were a minus, then we'd be able to factor this, but because it's a plus, we can't. So we can just use the quadratic formula with a equals 1, b equals negative 4, c equals 5, and that's going to give us lambda equals negative b plus minus square root, and b squared is going to be 16 minus 4ac, it's going to be minus 20, divided by 2a. So this is going to be 4 plus or minus, and this is now square root of negative 4, all divided by 2. Now in complex numbers, this is going to be 4 plus or minus 2i divided by 2. And so if I divide each of these by 2, that's going to be 2 plus or minus I. So we have our two complex eigenvalues. Now what does that mean? That's a matter that we'll explore a little bit in this class, but we'll explore it, if anything, much more in Math 256. Now let's try a 3 by 3, and in particular let's do a 3 by 3 that also happens to be diagonal, so we can get some verification for what we were told, but which was not fully justified to us last time about the eigenvalues of a triangular matrix. Okay, so let's say A is equal to 1, 3, 2, 0, 1, 5, and then we have 0, 0, 3. So let's say we had something like this for our matrix. Now because it is triangular, we actually already know the eigenvalues, but let's see how that would actually play out in a cofactor expansion. So A minus lambda I would be 1 minus lambda, 3, 2, 0, 1 minus lambda, 5, 0, 0, 3 minus lambda. And then if we were to do a cofactor expansion, let's say along the first column, then we could have, so the determinant, A minus lambda I equals 0. That's the characteristic equation. And now let's just look at this in its cofactor form. 1 minus lambda times 1 minus lambda, 5, 0, 3 minus lambda. So then actually technically I guess minus 0, according to the checkerboard, plus 0 equals 0, which gives us 1 minus lambda times 1 minus lambda times 3 minus lambda equals 0, which, because we're setting this equal to 0, I can multiply everything by negative just to make it more usual looking to me, and I'll rewrite it as lambda minus 1 squared, lambda minus 3 is equal to 0, which then leads us to lambda equals 1, 1, and 3. So we have multiplicity 2 for an eigenvalue of 1, and then we have 3 for the eigenvalue, and then we have an eigenvalue of 3 with multiplicity 1. All right. Now, some notes. Some notes of relevance when it comes to the eigenvalues of things. So here's a fact for you. The product of the eigenvalues, and here with multiplicity. So repeat the factors as necessary. Is the determinant of A. So that's a fact. 2. The sum of the eigenvalues, again with multiplicity, is the same as the sum of the entries along the main diagonal. And this number, this shared number that is the sum both of the eigenvalues and of just the entries along the main diagonal, this number is called the trace. It's easy to see why this would be in a triangular matrix, but it's not so easy to see why it would be in any others. So this is called the trace. And you write it, just trace, TR of A. Alright, and then third, the total number of eigenvalues and this is accounting for repetition, so allowing both repetitions and also complex eigenvalues. So repeated and complex eigenvalues will be n. It will always be n at all times. So the total number of eigenvalues, when you allow for repetition, will always equal n. This actually, for the record, this is a consequence of a fact that is called the fundamental theorem of algebra, which has to do with the number of solutions that a polynomial of degree n can have, and it turns out always have the same number of solutions if you allow repetitions and for complex values as its degree. All right, and then fourthly, so because of the way things shake out in a 2x2 case, where things are always simpler than they are in any other case, we can actually come up with a shortcut for the characteristic polynomial. As always, the 2x2 case is so small, there's some kind of shortcut available. So there's a shortcut. For the 2x2 case, to get the characteristic polynomial. So the characteristic polynomial which is the determinant of a minus lambda I, this happens to always equal lambda squared minus trace A times lambda plus the determinant of A. So for example, let's say we wanted to do something like like this. So let's say A equals, let's say 2, 3, 3, negative 6. Then the trace of A is the sum of the entries along the main diagonal. So that's going to equal 2 minus 6 is negative 4. As for the determinant of A, that's the familiar thing. So it's going to be 2 times negative 6 is negative 12, minus 9 is negative 21. And then what we're going to end up with here is then lambda squared minus trace of A, so it's minus negative 4 lambda plus negative 21 equals 0. So in other words, lambda squared plus 4 lambda minus 21 equals 0. And then that's going to lead us to something we can factor, and it's going to be lambda plus 7, lambda minus 3. And then that's going to give us lambda equals negative 7, and the lambda equals 3. That's our two eigenvalues. So this is a slight shortcut. It's basically not even a shortcut. It's not super relevant in solving this. However, it does lead one to often create what's called a trace determinant plane, and then you can use that for differential equations things. But we're not really going to get too involved in that. We don't need a shortcut for such a simple thing anyway. It would have been basically no more work to have found it by the more traditional method. All right, last note here. So similar matrices. So A and B are called similar. Are similar if there is any matrix P such that A equals P B P inverse. Now this, remember, we described this back when we first introduced determinants. This is called a similarity transform, and the determinant of these two matrices will always be the same. So what that means is that actually so will their characteristic polynomial characteristic equations, and therefore eigenvalues be. So so similar matrices will have the same determinant characteristic equation, or I should say characteristic polynomial, and eigenvalues. So for this reason, eigenvalues are called an invariant of the matrix, but that's not something we need to dwell on right now. But we'll see what the consequences of this will be in a later section. So that brings us to the end of our discussion of section 5.2. Thank you for joining me for this episode of Math 261. I will see you at the next one. Till then, bye.